So now we have trained some models and we can incorporate them into our whole system. As I said, we have a battery management system, and one part of this is the state of charge estimation. Let's put this into the model now and test it. So here we have some blocks that you can do that you can use to add these models into your simulation that are readily available. Like for the statistics and machine learning toolbox, you have special blocks, like for the regression ensemble predict or regression neural network predict that we saw, or if you had trained a tree model, you can use the regression tree predict block. So for the models, for every different models that you can train, there's also a different block that you can use to incorporate this model in your simulation. For the deep learning toolbox, it's the same. So you can, depending on what kind of deep neural network you've had, you can use a different block. So if it was a classification, use an image, or if it was an image classification, then you can use the image classifier predict, or here in our case, for the regression, just to predict. And then we also have some industry-specific blocks that you can use, because like the audio toolbox in itself has some machine learning, specific machine learning algorithms that are incorporated, and then you can use some of these specific blocks for Simulink. And this has been recent work, so you can see in which version these blocks have been added, and they're always added more blocks. But of course, you can also always just use a generic MATLAB function block in case this block, there is no block available for you for your machine learning model in question. So let's see how this looks like in our example. So let's open the system. And here you can see we have the 4 different versions, the extended Kalman filter, or the machine learning, so this small, here we have the tree that behaves really well. Here we have the deep learning feed-forward neural network, that was the smaller deep learning model. And here you have the LSTM model, like the one with the many learnable parameters that took a long time to train. And you can choose which output to use, or which model to use. Now we used all models, and we're going to compare the results. So let's run it, and let's look at the output. So here we have now the comparison of the different model. Like the truth, this is like from some real test data. Then we have the extended Kalman filter, the machine learning, and the deep learning models. And now you want to evaluate the performance. So you compare the output to the real output, and you get some root mean square estimation error, root mean square error. And the model with the smallest error is the best one. So once you've decided which one you want to incorporate, you can incorporate this in the full system level simulation. Or even all of those. And here you can see the state of charge estimation. CC, that's Coulomb counting, which is a very easy method, but you can see it's not very accurate. Although it depicts like the right behavior, there seems to be an offset. Neural network, extended Kalman filter, or the true value. True value is the green one. So you can see that the other ones are behaving quite accurately. But in the end, you want to run these algorithms on some target. There's a good thing that we can generate code from these models that you've trained. So depending on where you want to deploy on a CPU, on a GPU, or on microcontrollers, or on FPGAs. You can use the code generation for all of these. In our case, we wanted to deploy the state of charge algorithm on a microcontroller. So in the case of machine learning models, you can generate code like C or C++ source code that you can deploy on any CPU. In case of deep learning networks, you might want to use some optimization libraries, which will make sure that the inference of the network, so that the networks can run in an optimized fashion, so that they're pretty fast, and then optimize for certain targets. But some people don't want to do that. They don't want to depend on some optimization libraries. So there's always the option also to generate library-free source code, which you can then deploy on any CPU, including ARM Cortex-M. So that's what we did in our example, generating libraries-free source code for the deep neural networks. So here you can see how this looks like in MATLAB or Simulink. So here you can see the full system again. Now I can say I'm using the embedded coder to generate code. And there you have some options. You can choose the language, C or C++, or also which standard to use. And then for the interface, you can also say if you want to use an optimization library. And we set none, so library-free deployment. Then this is what we want to generate code for this subsystem. So this is only the state of charge estimation. And here you can see the result. So this is the, I think it's the neural network prediction. The deep learning network prediction function. And here you can see all these parameters that were trained. So you can see it's quite a few parameters that were trained for the prediction. And this is how the C code looks like. And here is the inference. So how all these parameters are then used to predict the state of charge for a given voltage, current, and temperature measurement. So this was the deployment part. So we showed you how you can create library-free source code from this prediction, from this neural network model that was trained before. Now, you can deploy this code now on the microcontroller or on the processor, and we can now also simulate the full system with this processor in the loop. So code is generated from the algorithm. It was deployed on this ARM Cortex board. Then we connect this to the full simulation, so the deployed code communicates with the simulated plant. Let's see this in action. Again, we have a video, and this is basically, it's the video from from the beginning. So yeah, target hardware resources that you want to use. Then you connect, and you can run this processor in the loop simulation, and you can see the output here. And now it behaves the same way. I think it's the neural network here that's running as before. Then you can see some results, so like the profiling. You can see how fast it went because this is probably what you're interested in, to know how fast will it be like run in the end in the processor. So like this, you could see that we could test now all the way. So in every step, when we did the AI model, you test it with the test data. In the full system simulation, you could test how it behaves, and also you can test how the algorithm behaves in the deployed version. So we've seen different AI models, the extent or different models to estimate a set of charge, the extended Kalman filter, the fine regression tree, which was this machine learning model. This one was the very, very small deep learning network, the feed-forward network, and then the LSTM. So you can compare these models now, how they behave, and then choose what you want to use. So for these steps, for some steps, there is some pre-processing effort you need to do. For the tree or the FFN, we had you needed to use average, you needed to add some more features. The training speed is very low for the extended Kalman filter because you don't need to train. Then the tree is very fast to train. The feed-forward neural network was a little bit slower, and the LSTM takes a long time because it has a lot of parameters that need to be trained. Then you also need to know, like, look at the interpretability. So if I want to now know why did the model behave in the way it did, you might want to be able to do that. For trees and extended Kalman filter, it's very easy because yeah, it's a very small model, so you can actually look at why was the result as it was. For a bigger model, it's harder, and for the LSTM, it's almost impossible to know why did it behave in that way. So it's very hard to debug. Then you need to look at the inference speed, like, so how long does it take or to predict the state of charge value for some input values. And here the LSTM is the slowest. Feed-forward neural network is very fast. And the extended Kalman filter is not very good in this aspect. Then the size of the model, because yeah, you need to deploy it to a processor, and some of them might be too big even to deploy in a processor, depending on what your target is. Like the LSTM is very big. And then of course the accuracy, so how well did it work? And the LSTM was really good, had the lowest RMSE. So this is an argument for using the LSTM. And then the other ones behave okay. So we've seen that the LSTM gave us really good results, but yeah, it's slow to run, and it's also very big. So it has it needs a lot of space on the target. There's something you can do to remedy that problem. So that is called compression. So that's a bridge between like these three steps. Like once you have the AI model and we want to deploy it, you might want to add another step, which is compression. And you can see what this means in an example. So let's say you have a model that has 400K learnables. You can compress it to a smaller model. There are techniques to do that while preserving the accuracy. So this is an example here from 400K to 30K down. So this is much smaller. And with this projection technique, it was possible to almost keep the accuracy of the model. So there's only a small dive in the accuracy. But then the model was much smaller than the original model. So this is really good. That also means that to run the model is like much faster. So that was then the inference time was like half of this fine tune. So this compression step might be something that you can do if you feel like, oh, my model is too big. but I'm really happy with the accuracy. And then if you do that with the LSTM model, you'll get an inference speed that's okay while preserving the accuracy of the model. There's nothing you can do about the training speed because the training, you need to do that before. And also the interpretability of the model doesn't get better, but the inference speed gets better. So to look at what we've seen these 4 steps to train and test an AI model and to test it also in the full system. We saw that compression can help you. If you have a big model that you would like to deploy on a target. And there's always this trade-off that you need to do. You see, like usually bigger models give you the better accuracy, but then they usually have a smaller or a worse deployment efficiency. So this is this trade-off for you to choose which model to use. And usually you try different ones and then decide. Yeah, so select and implement the optimal AI technique for your application. And always keep the deployment model, the deployment step in mind when you do that. So you always already know like what is the target and then what are sizes of models that are acceptable for my target. So what we've seen, how to build a virtual sensor using AI and how to integrate it into Simulink for system level simulation and code generation. And if we take a step back again on the big picture, we have seen how you can use AI with MVD in the different steps like reduced order modeling, reinforcement learning, for data synthesis, and for the virtual sensor, which we had a look more in detail. And so in summary, AI with MVD, model-based design. So there are many promising applications in the intersection between AI and simulation. We saw that AI models can be used to enhance simulation models. So that's a typical case, but also the other way around, that simulation models can be used to enhance AI models by generating synthetic data. And in MATLAB and Simulink, you can use one tool change to do both AI and simulation with seamless interaction in between. That's the end of my presentation. Thank you very much.